That's correct. Thank you very much. So I think you can hear me. Okay, so recommendation engines drive the world nowadays. They're absolutely critical in just about every business where products and customers intersect. And in 30 minutes, I'm going to try to do the following. There's a longer version of this presentation on YouTube. So if you look up Bit9 or AgensGraph and recommendation engine, it'll be the first hit. So it takes about an hour to go through it at a leisurely pace. So this will be a little bit rushed. So has any of you programmed in Cypher before, written any Cypher? Okay, 1, 2, 3, 5. And anybody heard of AgensGraph before? No? Okay, 2. Our own sales director has. That's really comforting. So AgensGraph is a graph database. It's built on Postgres, which is a relational database, a SQL database. And what we've done, Postgres is about 1.1 million lines. And we've taken the parser and heavily modified it so that in addition to understanding SQL, it now understands graph query language, Cypher, as well. So we get all of the stuff that comes with Postgres for free, all the ability to import from various different sources and ACID compliance and MVCC and granular access control and all of that stuff and high availability and PostGIS extension, all for free, and we just add the graph bit. Yeah. And so the language is Cypher. So I'm going to try to just cover some of these subjects here. And what is a recommendation system? They've been going for 25 years, and businesses find them to be the most valuable foray into data analytics. It's the biggest bang for the buck. You invest a very small amount in a recommendation engine and you get a load back very, very quickly. My definition is it's for each user, the product most likely to be relevant is what a recommendation system spits out. And then product can mean playlist or content or people or and so forth. Some of the figures are 15 to 35% increase in sales across a variety of industries. There are sources there as well. And 30 to 80% increase in screen time. On the right-hand side, you can see there's a flat earther, and he was interviewed a while ago. And it turns out that most of the flat earth community came to be attracted to the concept via recommendation engines. And there was a speech given by the guy who started the recommendation project at YouTube, who said that this was not their intention. It wasn't their intention to make YouTube an echo chamber where you would continuously just get re-hit with your own opinions time and time again. But that was a consequence of it. And it's difficult to read anything about AI that doesn't deal with the social impact as well. So that's one of the social impacts of recommendation engines. There are many others, so we have to be responsible. So on the journey of analytics, from descriptive analytics, which is basically Excel and sales charts and graphs and averages and sums, telling you that you sell more hats in the winter, going through this almost doctor's chart through diagnostics. Why is it? Because cold means more hats. What's going to happen next winter? Oh, we'll sell more hats. And then this concept of prescriptive analysis is writing the future. So if we could make it more cold, which is very topical now with climate change, so we all have an onus to bear in that really. So we're somewhere in this blue box. We're somewhere between predictive analytics, because a recommendation will tell you what people are likely to like or find relevant, right into prescriptive, because by offering them what they might like, they will buy as well. So you're really writing the future with a. Now there are two fundamental principles two really basic principles in all recommendation systems. And one is called collaborative filtering, and the other is called content-based filtering. And they're distinctly different. This system here relies on the fact that Alice and Bob both seemed to like a blue and a green product here. Although I know nothing about Alice or Bob, and I know nothing about the products. I haven't parameterized them in any way. I don't know their genders, their ages. I don't know anything about the products. I only know that Alice and Bob both like these products. And if perchance Alice likes this product too, which Bob has not experienced yet, then I should recommend this product to Bob. That's collaborative-based filtering. It leans on, it's interesting to hear so much today about knowledge graphs. This leans on one fundamental human principle, And that is that people who agreed in the past are likely to agree in the future. So the principle of work here is Alice and Bob have agreed in the past. Alice has made a new journey, and it's possible that Bob would like that journey too, or that experience. Now, content-based filtering is entirely different and demands that you parameterize the product. You can parameterize the people too, but generally you'll parameterize the product. So for instance, Spotify parameterizes songs based on 400 parameters. You know, the artist, the title, the genre, the beat, the beats per minute or whatever it's called, drum and bass, whatever's in it. I don't know where you get 400 parameters for a song, but it does. And then you simply say, okay, well, if Bob bought this product, I have to look in the parameterization space and find a very close product and recommend it to. And that's content-based filtering. Here you have a cold start problem. If John if John becomes a new prospective customer, because you know nothing about John, even when he makes one purchase, you're still in the dark about John. You have this cold start problem. Over here, as soon as John buys his first product, he buys a science fiction book based in the 1940s, blah-de-blah, yeah, you sell him, offer him the product right next door. Yeah, so based on your industry, you'll find one or other is really valuable. Every collaboration system, based filtering system, relies on a matrix. This is the starting point. And this is all of the data that you're going to use. You don't use any other data apart from this matrix. And the matrix rates customers on one axis. I won't be able to use my mouse, will I? know. It rates customers and products. And I've got a very small data set here. I've only got 8 customers and 10 products. And generally, this would be a very, very sparse array. Yeah, because take Amazon, like a couple of million products, a couple of billion customers. It'd be a horrifically sparse array. And graph databases are really good at sparse arrays. Because I have a node for my customer and I have a node for my product. And if there is a rating between them, only then will I have an edge. So it's super efficient from storing a sparse matrix perspective. This is my starting point. And where there are blanks, it means that that customer did not rate that product. Yeah? So I want to know what are the ratings for all of the bits that are missing. And if I know what they are, then I can find the product that's most highly rated by a customer that he has not yet bought. So if I wanted to fill in this line here, I have almost all this line, but I don't have these values here, and I don't have this value here. So I want to know, how would C4 feel about product 3? That's what I want to know. That's just to fill in that one little blob there. And then when I filled in this and this, I'll also know what is the favorite of these 3 products. Silly example, there's only 3 products he didn't buy. In real life, it's hundreds or thousands. Yeah. So I want to know which of these 3 products might he buy. Now, I know a little bit about P3. I know that C1 liked it 2, and C5 liked it 4, and C7 liked it 5. So 2, 4, and 5 are the 3 ratings that I have. What do I do with them? Do I add them? Do I average them? What do I do with them? Well, what I actually do with them is I take a weighted average. I want to compare the similarity of these customers, C1, C4, and C7. I want to understand their similarity to customer C4. I want to understand how similar these people who rated that product are to C4. And for the people who are really similar, I want to kind of scale up their preference for the product. And for people who are very different, I want to ignore how they felt about the product. So I really want to just zoom in on the people who are really similar to C4, because he's the guy I'm interested in at the moment. Okay? And the way I do that is I need to measure the similarity between customers based on what they rated or bought or whatever else. So the question is, how do I measure similarity between customers? And it turns out to be a pretty straightforward trick that's used time and time again in linear algebra in data analytics. I use a thingy called cosine similarity. So this describes one customer. This vector of numbers describes C1, and this vector of numbers describes C2. And I want to ask, how similar are they? Yeah. And what I'll do is I'll take the cosine similarity, which looks pretty scary, but this is cosine similarity. Over here is how I'm going to measure the similarity. What I'm going to do is imagine that both of them is a vector in a multi-dimensional space, 10-dimensional space in this, because I have 10 products. So each customer is a vector in that space. Now, if they're really, really similar, they'll be pointing in the same direction. And consequently, the cosine of the angle between them will be very close to 1. If you remember from your trigonometry, the cos of a small angle is 1. And an orthogonal angle like 90 degrees is 0. So if they're pointing in completely different directions, their similarity will be 0. And if they're really close together, they'll be 1. So immediately, I can measure how similar customers are. In my example, I wasn't able to use all 10 because I'm not able to draw a 10-dimensional vector space on a flat screen. So I'm just using these 3 values here. And to measure the similarity over there is a scary equation. The bottom bit here takes each of the thingies of the vector, each of these, squares them, adds them together and takes the square root. And you might recognize that as Euclidean distance or Pythagorean distance. That's just the length of that customer vector. So I have the length of the A customer vector, the length of the B customer vector as the 2 denominators. And then on the numerator, it's a thing called the vector product, the dot product, which is literally this times this, plus this times this, plus this times this. So I do all that arithmetic, and out pops my, my similarity matrix. So I've run this on each of the customers, and I found that these are the similarities. So C1 is really similar to C2, 0.7. Of course, C2, this is symmetrical, so I don't need half of this because it's symmetrical, yeah? And I don't need my leading diagonal because they're identical, 1. So again, my graph will store just this information, and this would generally be a sparse matrix. This isn't. In fact, I'm only missing 1 value, C3, C5. So that's my similarity matrix. Now I have the similarity between, do you remember I was interested in C4? And now if I go along here, or down here, same row, I can see that, well, C1 is kind of half, so he's pretty similar to C4. C5 is not at all similar to C4. It's 0.2. And C7 is quite similar to C4. So now I know I really care about how C7 feels, and I don't care so much about how C5 feels. And this will capture it here. This is how similar they are, and this is what C1 thinks of the product. This is how similar he is to C5 and what C5 thinks about the product. This is how similar he is to C7 and what C7 thinks about the product. I add them all up together and divide by a normalizing figure to keep it between 0 and 5 in this example. And that's it. And like for free, I have now rated the product with just using that arithmetic there. You can see that I'm really bringing a big number here because I'm bringing 3 from this here, 5 times 0.6. Whereas this, because the similarities are so different, irrespective of what that says, I'm not bringing a big number with me. I'm bringing 0.8. Yeah. So 3 from here, 0.8 from there. And I end up with 3.7. So that's 3.7 was in there. And this has told me that based on the collaborative base filtering, C4 will rate P3 with 3.7. That's as simple as it is. And then I do it for every other. Empty cell. Okay, so if I were to, for instance, what I've done is, to make it easier for people to understand, I've actually taken this and I've done all the arithmetic in Excel, because Excel is really straightforward to understand. So that's my raw data there, which I've taken in. And then I want to normalize it because I like numbers between 0 and 1. Yeah. So 1 is the most favorite product there, P8. For C1, this was his favorite product. He didn't rate these products at all. And his least favorite is probably 0.38 there. Yeah. So this is kind of now my starting matrix. It's the normalized version of ratings. Okay. Then I take the cosine similarity, which is really simple. I take the length of each vector, multiply them, and I take the dot product in the numerator and do the arithmetic, and out pops the similarity. And then the next bit's really simple. For every customer, say for C1, I want to know how C1 feels about a particular product. What I'll do is I'll go to every other person who has rated that product, and then do a weighted average based on the similarity to that customer. And what happens is I will turn up the people who are similar and value their opinions, and turn down the people who are dissimilar and almost reject their opinions. Okay, so this is the, so let's see, having done all this donkey work, I find that C1, for C1, these are the products he didn't buy. I've just marked them with an asterisk there. So of the 2 products that C1 did not buy, this scores 0.74 and this scores 0.25. So clearly I'm going to recommend the product P7. Yeah. Okay, so that's what the Excel looks like, and anybody who's interested can just jot me an email, and I'll be able to send you these files along, so you can work along with your Cypher code. And this is the Cypher code, which is pretty straightforward. First thing I do is I just I drop some stuff. I delete graphs just so I can start from a clean starting point every time. I create a little table, and I'm going to pull in my values. I'll show you my values. The raw data values here are here. So that's my data. Customer 1 bought 4, or rated 4 on product 1, 7 on P2, which is exactly that data. I just pivot tabled it. It's exactly the same as this table here, yeah. Okay, so that's my starting data. And I'm going to load this into a table called purchases. I'm going to create a graph and set the graph path so that when I run Cypher now, I'll be accessing the right graph. I create V labels and E labels. V labels are things that, for a collection of nodes, you can give them a label. So I'll tell you, I'm going to have a cluster of nodes that are called customers. There will be 8 of them. I'm going to have a cluster of nodes that are called product, and there will be 10 of them. And I will have edges between them whenever a customer rated a product. I will have an edge, and on that edge, I will have the rating. Yeah. So then I'm going to load from that table of data, of values. For each row, I'm going to read the customer name and the product name and create a node for each of those. So every row will create a customer, if it doesn't already exist, and create a node. And then I'm going to create an edge called buys that's going to connect the customer node to the product node. Yeah. And that basically now is storing my rates matrix somehow or other as a graph. And what I can do is I can show you what this will look like. So first of all, actually, I'll just give you a little introduction to Cypher ASCII art. So the way Cypher works is it's got this really artistic way of representing what it's trying to say. So you have a customer rates, I said buys, rates, whatever, a product. And this is the base notation. Nodes are in round brackets, and relationships are in square brackets. And then you can have a direction on the relationship if you want to as well. You can leave it out, or you can even have it here. So this is a node, and this is a relationship between them. And either the node or the relationship can have as many properties associated with it as you like. You can have a big JSON document, you can store arrays, you can store bit images, you can store anything you want, and as much data as you like. Fine, let's talk about labels. So this one here specifies that I want to talk about nodes, but only the nodes that have the customer label. This is only nodes with the product label. And this is only relationships with the buys label, or rates label. And I can also identify these customers that I identify. I have identifiers to reuse them. If I want to refer to the same customer time and time again, I can apply identifiers for the nodes and the relationships. And finally, this is how I populate properties into the node. This is an identifier. This says the node customer node. And this, in between curly brackets, is where I put in properties. And it's as simple as saying name, C1, and I could just comma and put in as much data as I like there. Same with relationships, I have quantity as 4. And so that's the language of Cypher. That's what it's going to look like. And if I look at what I'm going to store in a moment, this is the first thing I'm going to create. This is what's called the metagraph, or the schema of the graph. I'm going to have customers 8, I'm going to have products 10, I'm going to have rates here, or buys first, then rates, then these later we will create recommendations. In other words, fill in all the blanks on that first matrix. And that this is the cosine similarity, and of course the similarity is just between customers. I could also, by the way, run similarity on product based on the people who bought them. So you can turn that matrix on its head and just rerun the code, and it'll produce something really interesting as well. It is a it's a bizarre form of collaborative-based filtering with the things that products who like people in the past will like the same people in the future. It's just a weird way of turning on its head, but you can do that, and that's my similarity. So that's what we're going to be creating in the Cypher. I'm conscious of your time, so I don't want to keep you from lunch either. So if I go back into my code here, 8 minutes, okay. Okay. Fine. Okay, so let's do this. I'm going to go into, this is what, oh, you can't see that very well, can you? If I was smart now, I'd be able to change the font size and that. I'll do that right now. Properties. Font. Sorry about this, I should have done this ahead of time. Let's try 28. Okay, that's better. You can see that now, maybe? Okay, so I'm going to drop in my code here and run it. Let's run off the screen. Okay, so what I did there, I ran that code. It inserted 18 vertices, or nodes. What do you think are the 18 nodes that I inserted? Customers and products. So that's 8 customers and 10 products. And I inserted 49 edges, because that's how sparse my matrix was. So I have 49 instances of this customer rated that product. Okay, so we're everything seems to be working well so far. I'm surprised. I normally don't get this far. Okay, so now I'm going to create the normalized rates version. This is the normalized version of it, just between 0 and 1, because data scientists love stuff between 0 and 1. Okay, drop that in. And again, I've created 49 normalized rating edges. Okay, right. Now, the next thing I'm going to do is I'm going to create the cosine similarity. The first thing I do is I don't know if we don't really have time to go through the code, but I'd be more than happy to troll through this with anybody. Here I'm finding everywhere where a customer rated a product. And this is just a tiresome way, because that's the way Postgres is, a tiresome way of finding the length. So I'm going to square them all, I'm going to add them up, and then I'm going to take the square root. And this just does it. You pass one result on to the next. I square it, I sum it, and then it takes the square root. So, and then I'm going to store the length of each vector in the node itself. So, and then I'm going to do my cosine similarity. And you can see that I'm going to do my dot product here on the numerator. I'm going to do the products of my lengths as the denominator, then to do the division, and then create another edge which will link a customer to a customer. If you look, they're both customers. See, X and Y are both customer. I'm going to link a customer to a customer with an edge that contains the similarity. Okay, so let's do this. Okay, don't worry about that. I did it. It's just I grabbed a comment as well, or a half a comment. Okay, that worked. And finally, now we're going to create the recommendation. And first thing I'm going to do is I'm going to find, I don't know why my mouse drops like that. It's like an episode of Simpsons. I'm going to find every single customer and every single product. So now I've kind of got a three-dimensional thingy going on here. On the front face, I have customer and the similarity. Yeah. So that's what I have in my front face. And then in the depth, I have product. And I can go to anywhere in this space. And I can sum, I can aggregate across any direction in this space. So that's what I'm doing here. In Excel, I have to do this in multiple tables, because it doesn't do three-dimensional tables in Excel. This does any dimensional tables that you like really, really efficiently. And in fact, this is the entire code that creates the recommendation. That's it. And it would be even shorter if you could do a function of a function of a function in Postgres, which you can't for performance reasons. because they want to. So I'm going to create all my edges here. So I'll just pop this in here. Run it there. And this returns to me what I should recommend. So C1 will be recommended P7 with that score. And it's sorted by, I've taken the things, the products that they didn't purchase and rated them from highest rating to lowest. So let's say take C2 will recommend P6 at a value of 0.8. And if we hop over to the Excel spreadsheet, recommendations for C1, 0.74 was for P7 and P5, and C2 recommended P6 at the value of 0.8. So we're getting the same results from our Cypher and our Excel. Okay, so the next thing to do would be just to consider how I would improve this, because it is a little bit naive. Now, I completely get that. The first thing I'd do is I'd use cosine centrality on ratings. And the reason for that is, if a customer didn't rate a product, I essentially took that to be a rating of 0. And that's just not fair. Yeah. Number one. Number two, by using cosine centrality, avoids no rating, but it also smooths harsh and easy raters. Because if everybody gives it, if one guy gives everything a 4 and a 5, then I can center that and say, okay, he doesn't like the 4 and he likes the 5. If you get everything in a 1 and a 2, he likes the 2. 2 means I like it, and 1 means I don't like it. So you'd center everything up, and that's the centered version. All I do is take the average and subtract the average from every rating. So I end up with negative ratings and positive ratings, and 0 is middle of the road. And now, not judging the product at all is middle of the road, rather than disliking it. Okay, I'd also categorize products, which is really easy. I could do it in the code that does the recommendation. I just say where category equals something. So it'd be much better to do it per category rather than just doing it across the entire product set. If I'm able to categorize my data. How would I categorize my data? Run this in reverse, and I would identify categories immediately for me. The other thing I would do is for consumables, I'd show products already purchased, of course. Yeah. For books, music, I'd show similar products. And the next kind of level of artificial intelligence that you could introduce, not quite artificial intelligence yet, but you could say, okay, this is a product, and this is the final recommendation for that product for customer. I'm going to factor in things like business things like stock and margin and a whole host of other factors. So for instance, say the sales director is saying, look, stock's way too high. I really want to we want to get our stock down. I'll even sacrifice margin. Just get me my stock down. Stock holding's too much. Then this K1 will get turned up and this K2 will get turned down. Next month he says, oh no, margin's king. Margin's king, don't care about stock. Then I would push the products in which the margin was the highest, not the products that my stock holding was the highest. So I sum all of these. These are just, these are business-wide parameters, only a handful. And these are per product, yeah? What's the stock like on the product? What margin do I make on the product? And then you sum these and you take the original recommendation, multiply it by your new factor, and this is the final recommendation. And if you can do A/B filtering, so you have like a recommendation engine over here with 0.6, 0.2, and 0.7 or something, and another recommendation over here with 0.7, whatever, you compare their performance. And that way, now you're in the world of artificial intelligence, you can do gradient descent and finally zoom in on a set of numbers that maximizes whatever it is you want to maximize. So they're the kind of the next steps that I would take if I was going to do this for a real business. I've helped one real business do this, and he's delivered about, on a business that's a 4% margin business, he's trickled his margin up to about 4.2%, so significant return on investment. And it's all developed in literally 20 lines of Cypher. So that's how to develop a recommendation engine using Cypher. Any questions? Yeah.
The Similarity filtering algorithm, it has like a limit to sparseness. So I think if your matrix is like over 95% sparse, it doesn't really work anymore. How does it behave in like graph database? Do you still have that problem?
Well, the real advantage of it being very sparse is that it's a perfect candidate to be stored in a graph database. because things only exist. I don't store nulls anywhere, ever.
Is there a limit to how small it can be?
No, there isn't, no. What you could do is, you would have to get clever if there are just way too many products and way too many customers. You'd have to get clever and say, okay, I'm only going to deal with, say, cosine similarities above 0.7. So you don't have to do the arithmetic for anything below that. So you literally are only picking the cluster of customers that are really close to you. So that would be one optimization. So you'd need optimization if you have 2 million products and customers. Yeah, you would need optimization for sure. Yeah.
Any others? Back in an hour at 2 o'clock. Thanks very much.
Thank you.